talking to you about reinforcement introgression and their impacts on the diversification of mate choice and sexual signals. So some of the reasons that I think mating traits are really important and interesting to study are that, first of all, who you mix your genes with has consequences for your fitness. So here in this hypothetical butterfly population, we have a couple of different kinds of males that produce different kinds of offspring. And if the female chooses to mate with this yellow male, her offspring are going to suffer increased predation from this blue jay as a result of her mating decision. Mating decisions can also affect gene flow. So whenever we have preferences for a particular sexual trait and orders that express that sexual trait, this can lead to a sort of mating between those orders and those choosers. And the corollary of that, and that sort of mating and gene flow among those groups, is that we would expect reduced gene flow between porters and choosers where the preferences and the sexual signals are mismatched. So when this gene flow is reduced, this can be important because that can potentially promote local adaptation and even in some cases potentially speciation. Whereas when mating decisions promote gene flow, this can potentially homogenize traits between populations, collapse species boundaries, or introduce novel traits in populations. So some of the main focus of my work is trying to understand how do we get diversity in mating traits, and what are the consequences of that diversity for all these processes that I just mentioned. So today what I want to talk to you about in particular is what happens to mating traits when individuals risk hybridization. So here in this example, we have a population of conspecifics where there's variation in these quarters and their sexual traits, in this case large spots and small spots, and variation in choosers and their preferences. So we can see that mating with a large spotted male produces more offspring, so we might potentially expect preferences for large spots to increase in this population. However, if this population co-occurs with a heterospecific that also has large spots, that preference can lead those choosers to then incidentally hybridize with that heterospecific. And in this case, that is resulting in no offspring. No offspring. So that would actually potentially lead us to the opposite prediction that preferences for large spots are actually going to decrease in this population due to the risk of this costly hybridization that they incur. So this can be important because this can lead to the evolution of different mating traits in populations that face different levels of hybridization risk. So here in allopatry, where there are no heterospecifics and no hybridization risk, we see the evolution of preferences for large spots because of the high quality of those mates. And then here in sympatry, where individuals are at risk of hybridization, we see the evolution of preferences for small spots. However, there's often variation in natural populations beyond a simple and hybridization risk beyond a simple sympatry allopatry binary. So we can ask what would happen to mating traits in a population that's intermediate between these two and hybridization risk. So in this intermediate hybridization risk population, one possible outcome that we might see would be the evolution of preferences for an intermediate spot size that's balancing the benefits of mating with large spotted heterospecifics or conspecifics with the risks of hybridizing with the large spotted heterospecifics. So that leads us to this idea of frequency-independent reinforcement, which here I am defining as mating trait values that vary among populations depending on the cost or risks of hybridization in each population. So this can be an important phenomenon because it may explain how mating traits can potentially diversify in natural populations that risk hybridization, and also this could potentially even have consequences for gene flow and speciation. And I'll talk about the potential consequences for gene flow later in the talk. So I evaluated whether there's frequency-dependent reinforcement in spadefoot toads. So Spea multiplicata is a New Mexico spadefoot toad, and that's my focal species, so I'm going to be talking about multiplicated traits for the rest of the talk. And multiplicata Spea multiplicata co-occurs with Spea bombivorans in this region of the southwest U.S., here in sympatry. And we know that in allopatry, over here in western Arizona, females tend to prefer faster conspecific calls than they do in sympatry. So we know that these faster calling conspecifics fertilize more eggs, they father offspring that are larger at metamorphosis, and they father more adaptively placid offspring, which you can read more about in this recent work from my lab mate Pat Kelly and colleagues. So we have some evidence that this preference for fast call rate is getting them conspecific mate choice benefits in allopatry. We also know that in sympatry, females tend to prefer slower calls, potentially because it helps them avoid hybridization with Spea bombivorans. So Spea bombivorans and F1 hybrids between the two, they both call faster than our focal species, Spea multiplicata. However, hybridization between multiplicata and bombivorans does occur in sympatric populations. So this is mostly driven by Spea bombivorans female behavior. So I don't really have the time to get into that story today, but it's very interesting, and if you want to hear more about it, you you should go to my lab meet Catherine's talk on Tuesday in room 551. It's a very interesting story. But this hybridization does occur in sympatry, and it has negative fitness consequences for spare multiplicata females. So hybrid offspring are sterile, and females are low fecundity. So this hybrid mating is going to give an offspring of very low reproductive success. And I additionally want to point out that because hybrid males are sterile, in these populations where hybridization occurs, females actually incur a greater fitness cost for mating with hybrids than they do even for mating with heterospecifics. So they can encounter a lot of different risky situations in these populations where hybridization happens. So the frequency of longifrons, heterospecifics, hybrids, and backcross males does vary among populations within sympatry. So that raises the question of whether the risk of hybridization is going to predict mating trait values across these populations. To evaluate this, I measured female preferences for 102 females from 13 different populations in sympatry using two-choice phonotaxis tests. So what I did is I gave the females a choice of a faster call that's still within the range of natural call rates of their species, but on the faster end of that range, which is going to be closer in terms of call rate to hybrid and heterospecific calls, and a slower call, which is again within the natural species typical call rate range, but farther away from heterospecifics and hybrids according to call rate. The other thing that I did was for each of these female populations, I measured the hybridization risk in their population. And to do this, I used 10 SNPs that are indicative of species identity between multiplicata and longifrons, sampled 50 or more individuals per population, and used this to calculate a genetic index of introgression in the genetic background of these individuals, and then an average for the population. So this x-axis is this genetic introgression index, and as we get higher over here, this is indicating more introgression in the population and genetic backgrounds that are more heterospecific-like. Versus over here on this end of the axis, these are genetic backgrounds that are more multiplicata or conspecific-like. So hybridization risk increases along this axis. So when we look at what the female choice data are doing, each color here is just arbitrary for a different population. And females on the top here shows fast calls, and on the bottom shows slow calls. And what we find is that the hybridization risk by this genetic introgression index is a significant predictor of female preferences. So females in populations with high risk of hybridization tend to choose these slower calls that are more different than heterospecifics and hybrids, and then females in these populations over here that have much lower hybridization risk tend to prefer faster calls. So we do have evidence that female mating preferences among populations are predicted by the risk of mating with heterotypics. So when we have this divergence in mating preferences among populations, this raises the question of whether this might reduce interbreeding between these populations because we have divergent mating preferences among populations. So whether this does reduce gene flow or reduce interbreeding can depend in part on whether the male signals and the female preferences are showing similar patterns among populations. So I'm going to explain what I mean by that in just a second. Okay. So back to our hypothetical butterfly population, here we have a low hybridization risk population like allopatry, where we have preferences for these large spots, and a high hybridization risk population with preferences for small spots. So we have divergent preferences, just like we do in spades and toes according to hybridization risk. So one other thing that I've shown in this figure is I want you guys to notice that the male traits are doing what the female preferences are doing in each population. So wherever females are preferring small spots, that's what the males have, and wherever females are preferring large spots, that's what males have large spots. So this means that this mismatch between populations in terms of quarter signal and chooser preference is going to prevent interbreeding between these populations because a migrant would be unsuccessful here and rejected by these mates. However, if we look at a scenario where there's still variation in quarter sexual signals in these populations, even though we still have divergent preferences, this is no longer going to reduce interbreeding between these populations because some of these migrants are going to be successful and not rejected by these mates from other populations. This kind of it shows how whether frequency-dependent reinforcement starts disrupting interbreeding between populations depends on whether the preferences and the signals are covariant among populations. So to evaluate this for spade-foot toes, I needed to look at male calls, which are the sexual signal in this case. So to do this, I evaluated call rate for males from 21 different populations. I used field recordings of male calls running 1996 to 2018, and this gave me a data set of 541 multiplicata male calls. And then I evaluated population hybridization risk the same way that I did for the female preferences that I had talked about earlier. And data was available for 14 populations for this analysis. So here's the data that I'm showing showing you are just call rates across different populations. So I just wanted to show you that there is quite a lot of variation in call rates among populations. However, when we look at that call rate and relate it to the hybridization risk in these populations, we actually find no relationship between male call rate and hybridization risk in populations. This is not a significant predictor of call rate. So this is kind of surprising, right? So just to remind you what the females are doing, females in these high hybridization risk populations prefer slow calls. Females over here in these more allopatric-like low hybridization risk populations prefer fast calls here and slow calls here. So usually what we would expect is that these preferences are generating selection on male calls and that male calls will be covariant with those female preferences. But that's not what we're seeing here, right? There's no relationship between hybridization risk and call rate. So the female preferences and the male signals are doing different things. So it's not exactly clear what's going on here, but I think a really good candidate to look into would be introgression from bombifrons. So as I explained earlier in the talk, this heterospecific does regularly hybridize. It's driven by the heterospecific female behavior. So these genes are getting into this population. And because heterospecifics and F1 hybrids both call faster than multiplicata, it's possible that call rate alleles from this faster calling species are getting into this species and sort of counteracting the effect of female preferences, pushing the call rates down, and then introgression pushing the call rates up to give us this flat line. So that's something that I'm interested in looking into. But to sum up, multiplicata female preferences for conspecific signals are predicted by hybridization risk in a population, so we see evidence of frequency-dependent reinforcement in female preferences. However, male signals do not follow this pattern, which brings up the question of whether introgression from bombifrons is potentially counteracting selection for female choice in this system. And I think this is an interesting case because it shows a situation in which sexual selection is promoting diversification of these mating preferences. So we see diversification of mating traits within species. And a lot of the time, when we see diversification of mating traits within species due to sexual selection, this leads us to hypothesize that this could potentially be involved in the initiation of species proliferation, right? But in this case, we see that that's probably not going to happen, and we see kind of a potential reason why that's not going to happen. So we still have diversity within species, but that's not likely to promote species proliferation because of the lack of co-variation of these female preferences and male signals. So I'd like to thank everyone for listening, all of my funding sources, and then all of the wonderful help that I've had from my lab, my community, undergraduate assistants.
Yeah, I have a question about what you were talking about with the males. So it sounds like a pretty elaborate hypothesis to say that it has to do with introgression. I wonder if something more simple would be that, males don't have any cost for having the wrong call,
Yeah.
Maybe that there's still enough individuals to mate that even if you have the wrong call, you still are somewhat successful.
Yeah, that's definitely something to think about. So in these